topic that is power oscillations here. And as shown in this figure, what we have actually some masses. So these are some weights actually, and these weights they are uh, tightened through a rubber band, and then they are fixed to they have a fixed element rubber band. At one end you have a weight hanging, and the other end of the rubber band, it is now fixed to some wall, or you can consider. Now this sketch analogy is very similar to a large network, and for which you can consider that let's say you have several capacity of generators. You have 200 MVA capacity generator, you have 500 MVA capacity generator, you have 1000 MVA capacity generator. So you have several of the generators, and these are interconnected through a line, transmission line, and then they are connected to their respective loads. But all the generators in the system, they are interconnected, and then they have a power flow in the network. But now uh, in this interconnected system, for a amount of the power flow uh, to the load connected, we want the voltage, and again we also want the frequency to be maintained constant here. Now if we consider some amount of jerk, let's say you apply some disturbance on the weight mass with a B here, so on. So if you apply some disturbance, as a result, what would this rubber band will have some oscillation here in among themselves. But again, tendency to oscillate, that means whether you have more oscillation or low oscillation, it will depend upon what is the weight of these masses here. And as such, with this analogy representation, what we can consider that these weights, they are the generators here. And again, these generators, they are of different capacity, and they have a different inertia constant. So you can say that some generator are lighter in weight, and some other generators being of larger capacity, they are heavier in weight, mass. Then again, this rubber property of the rubber band, that is the elasticity, you can say, it represents the transmission line, and then the transmission line, it has the inductance here. So that means we can hear the property of these rubber bands in terms of inductance of the transmission line. So if we apply some disturbance on generator 1 or generator F or generator E or D, then how do these generators, so they oscillate among themselves? That is important here. Now power system, in fact, usually it will have some period of oscillations, and it will add, as because we have a load flow, and if there is a change in the load disturbance or the change in the generation in the power plant, in that case the power system will try to adjust, or that means it will try to change to a new operating point and attain a equilibrium condition. So that means it will try to adjust to the new operating point and make the system or maintain stability at new operating point. Right now, following these disturbance applied in the system, we can say that if the amount of the disturbance applied is small, then the amplitude of oscillations will be also be small, and then again these oscillations will decay down in a short time period. So that means if you have some, let's say, applied some disturbance on this mass, then it will oscillate for few cycles, or let's say for few seconds, right? And then again after some time you will find that the oscillations have settled down. So that means in the same way, if you have applied some disturbance to the generator, there would be an oscillation, there would be a perturbation, right? And then again, depending upon the system, characteristic and then again the control action that we can apply. It is possible that these oscillations will decay down after some time. But if in case that following the disturbance, if it is a large disturbance, and then the amplitude of oscillations will also be large. That is one case, or otherwise, following the disturbance, the oscillations do not settle down. That means the oscillations do not decay in a short time frame. And we can say that oscillations continuously, there is a continuous oscillations after the disturbance. So that means we have, let's say, a sustained oscillations. Then in that case, we need to have some control applied. So thus the attention is required, particularly for those oscillations which are of larger magnitude or those oscillations which are of sustained nature. So that's otherwise the system may become unstable following the disturbance when it changes to the new operating point here. So this is one, that's the typical system that we have it in our power network. Now, to analyze this form of the oscillations, and mainly we are talking about the rotor angle oscillations. Such we have here, we want to analyze the transient stability. Now, what is transient stability? By this word, we uh, we want to study, we want to know, we want to determine uh, whether we are able to maintain the synchronism operation of the system or not. So that means if we say that if the amount of the disturbance applied is large in the network, then we want to study whether the system will remain synchronism. That means whether the system will maintain its stability or not following this large disturbance or not. So this is what we want to analyze here by saying the word transient stability. Now, in most of the cases for the disturbances, these oscillations, such oscillations will be of higher magnitude, and that means you have one operating point, and because of the large disturbance, the system will change to the new operating point, and with the new operating point shift. In that case, the equations, because we consider a small disturbance, and for the case of a small disturbance, the system equations can be linearized. But since the governing equations for the system, they are of nonlinear nature, and following a large magnitude of disturbance, thus the governing equations, they cannot be linearized here. And thus, whenever you have an oscillations of high magnitude, system governing equations, and thus that cannot be linearized here. And as such, we need to have solution for a single equation, so this which will be as a nonlinear form. Now here we have one of the method to analyze the transient stability, and that method is referred as equal area criteria. Now this equal area criteria, in fact, it is from P delta characteristic. We will study, discuss in the later slides. But as the name says, equal area, that means in the P delta characteristic, you have two different area defined now. And saying that if we say the two areas defined are equal, then it will be stable. And if the two areas are defined are unequal, then it will be unstable. So as such, in fact, in this method, this is one of the quickest method for determining whether the system is stable or not. This is one of the best method, but and this method is based on what we say as acceleration and deacceleration. So we defined one area uh, saying that you have energy stored, and if energy which is stored if it is released out for the new operating point, then in that case, whatever the energy which was gained following the disturbance, if it is released out, then in that means the system will get to new operating point in a stable way. So in fact, this method is a graphical representation uh, for energy storage in the rotor to tell you whether the machine is stable or not following the disturbance. And but there is a limitation here. Uh, the limitation is that this machine has to be using this method. I mean, the machine has to be analyzed as a single machine connected to a large network. So what is said that the method is applicable for one machine, one generator connected to an infinite bus system. So that means a one machine connected to a large network, or you can say it as two machine system basically. It can be one machine and another machine. So you have a smaller machine and a larger machine, and then you want to analyze the stability following the method as referred in the equilibrium criteria. So, but it cannot be applied for a multi-machine system. By the word multi-machine means more than two number of machines here. So if I say that you have a network and you have generator 1, you have generator 2, you have generator 3, 4 and 5 and so on, and let's say that you have some disturbance either nearby generator 1 or generator 2 or generator 3, and then you want to say that whether generator 1 is stable or not, whether generator 2 is stable or not, or generator 3 is stable or not, and so on. So using this method, we cannot say that whether the generator 3 is stable or not. We can say only generator 1 and generator 2. So in fact, in this case, this method is applied only considering that there are two machines only. So if you want to analyze if in a 5 machine network, so let's say that you want to analyze, if I say 5 machine network, and then since the method is applicable for two machine system, then you will say that let's say generator 1 and remaining generator 2, 3, 4 and 5, they are as a one large machine. So one large machine comprising of generator 4, generator 2, generator 3, generator 4 and generator 5. This is one large machine with respect to generator 1, which is a smaller machine. So in that case, we can analyze even in a multi-machine system. So but considering the system as a two machine system here. So that's that is the some characteristics of equilibrium criteria, or you can say the limitations of the equilibrium criteria method for analyzing the stability here, transient stability here. So we move to the next slide here with this introduction to the method. Now, uh, with this slide, remember here we have so many things to discuss, and then we will discuss them step by step. Now, we said that we have the transient stability analysis and we follow the method that is equilibrium criteria. And we have this P delta characteristic here, right? And this is your P delta characteristic, and this is your PE, basically electromagnetic power. And on this axis, we have the delta of the rotor, that is angle here. Now, we will consider the case because disturbance could be of any form. So here we have a case disturbance that is change in the mechanical power here. And we have the first one, the initial condition. Now at initial condition, what we get is this one. So we let us say that mechanical power PMO is this one. This is so mechanical power in the system is constant here. Mechanical power from the turbine is constant here, right? And with this case, what we find here that when we have the initial condition, so PMO is equal to electrical power, electromagnetic power at this point here. So this is the initial condition now. And in that case, the operating angle for the generator is delta naught here. So at the point A, PMO is equal to PE here, right? And as we said that let us change the disturbance. So we apply a disturbance of change in the mechanical power. So PM1 now. So we have a sudden increase in the mechanical power. Let us consider that, though uh, you cannot suddenly increase the turbine mechanical power, but let us consider for the time being. So we can apply a sudden change in the turbine mechanical power to PM1 now. So we have a increase in the mechanical power now. Now, so in this case, what you have it here, this one. Now, this is the change in the mechanical power given by this. So now mechanical power is suddenly changed and it is maintained constant now. Now with this disturbance, we want to analyze how the rotor angle will change its dynamics here. So now this is the turbine mechanical power change here. Now here we define one of the area, this one. We will discuss more in detail in the later slides. So here we define one of the area here, right? And now when it was this one, it was the PE and equal to PMO, right? And now suddenly you have increased turbine mechanical power to this line, which is a constant now. Now with this area defined, we call it as area 1. And for this case, what you find here that, because we said that turbine mechanical power is suddenly increased here. So momentarily PE is here. PE is at point A, and then suddenly you have increased the turbine mechanical power to this one, to this magnitude. And as such, PM becomes greater than PE now for this case here, right? Now this is the area 1 here. This we will say the area 1 now, right? And in this case, now from the relationship of swing equation, PM minus PE. So PM is greater than PE. So PA, accelerating power, PA is positive, and as such, the rotor will accelerate here. So whenever, that means if PM becomes greater than PE, the accelerating power uh, is positive, and the rotor will accelerate. Remember one thing, in this case, when we have changed the turbine mechanical power, we have assumed that electrical load is constant. We have not changed the electrical load at that instant. We have changed the turbine power, but the load, electrical load is constant, and that's why you have PM greater than PE, and thus accelerating power is positive and the rotor accelerate here. And now, if you have the PM greater than PE and rotor accelerate, that means rotor speed will it will increase, and as a result, what happens? Rotor angle will now move towards this side, on this line actually, right? And because of this, rotor angle will now continue to increase here, right? And it will be, let's say, I will discuss more in detail later on about this stuff 4. So what will happen, that rotor angle or the rotor will keep on increasing. So it will reach up to this point, but suddenly again the rotor cannot stop because the rotor has the inertia, right? But and then it is possible that rotor crosses this point. We'll discuss more in detail in the later slide when it crosses here. So what will happen? The rotor will increase beyond this, and then it will increase, let's say, up to this angle now, right? Yeah. And then in the next, what you find here, that here we have defined another area. It is this one now. So that means we have one area here, and we have, in fact, this is the area 2, and this is your area 1 here. So now in this case, when the rotor angle has increased beyond the point B, when the angle has increased beyond the point B, what will have, what you say in this range, in this point, what you have here, electrical power is more than mechanical power, because mechanical power is constant here. But beyond the point B, on this line, electrical power is more than PM here, right? and this is your area 2 here. So what you have it here, electrical power is more than Pm. And now from the swing equation point equation, Pm minus Pe, and now Pe is greater than Pm. So that means Pa, accelerating power, what we have said, it is now with negative sign. It is what we have negative sign. So thus now the power, that power is actually deaccelerating power, and thus the rotor will accelerate. In fact, beyond this point, Pe becomes greater than Pm, and as such, rotor will continue to increase up to this point because energy is stored here. Because in this region, Pm is greater than Pe, so energy is stored, and the rotor accelerate and increases up to angle delta 1. But rotor continues to increase up to this point. All right. But when the rotor angle increases beyond this point, that means delta 2 greater than delta 1 region. So when the angle increases beyond this point, what happens? Pe becomes greater than Pm, and thus rotor angle will continue to increase till you have, because thereafter you have deacceleration here now. All right. So in this region, you have a deacceleration because Pe becomes greater than Pm here, and thus you have two area. So if in case rotor continues to increase up to the angle delta 2, where it has all its energy released, because in this region you had the energy stored because of acceleration, and in this region all the energy, because in this region it will deaccelerate, and if in this region or whatever the energy which was stored gets released, then it will come back over here because mechanical power is constant here. So thus here we have two different areas, area 1 and area 2. So area 2, as in this case, is the deacceleration area, and area 1 is the case where you have acceleration area, right? So it is now again, now rotor will deaccelerate here, right? It will deaccelerate. It is possible that rotor has, that means rotor is now swinging. Rotor has swing to the maximum position of angle. As in this case, rotor has swing to the maximum position of the angle, and then again because of the deacceleration, again it will come back. Rotor will swing to the lower side here now. It swings back. So again, when it swings back, what you find here that in this case Pm is more than Pe now. So again it will accelerate here again because Pm is constant, and as the rotor crosses the point B here, then in that case crosses downward, I mean along this line, then Pe is less than Pm, and thus the what you have here, rotor is accelerating. So again the rotor will accelerate. So there will be a swing, there will be a continuous swing across this point here. Finally, whatever the energy which is stored, and it gets released in this area here, and then finally the rotor will settle down to the point B here now. So again, that means rotor swings to this side, and then finally it will come back to the new point here. That is your point B. Right. So that's what we understand here, that because of the disturbance, suddenly the mechanical power is increased, rotor accelerate, but rotor accelerate, it does not stop the point B. It continues to oscillate, it continues to change the angle position up to the point D here. But as it crosses this point, you have a deacceleration, so it comes back here now. And again, when it crosses this point, what you find, again the energy is stored because there is acceleration here now. Then again further it will go the outside in the area 2, and then again it will come back. So depending upon the magnitude of disturbance, right, whether the disturbance change in the power here is large or is small, so this energy is stored, and the release, that means storage of energy and the release of energy, it will, during this period the rotor angle will oscillate here, right? I explained this point more in clearly in the later slides. Right. So finally, you will find that rotor will settle down. That means in this case, delta rotor angle is changing with respect to time here, and it will settle down at this point here. This one, the point, and that will be the new state of equilibrium we say, because at the point B, PM will become equal to PE, and the rotor will not further oscillate here along this point. So this is your new state of operating. So with the angle increase of delta 1. So angle delta 1 is now more than delta 2. So now what you find here, PM has changed, and thus the electrical power has also changed, because now you have more electrical power output from the generator, and it is being supplied to the electrical load here. So this is, so the initial operating point with this one, and now the change operating point is this one. And if the rotor settles down to the new operating point, that means the system is stable here. Right now, again,
Sir, sir,
yes.
sir, if we are not changing the electrical load, then how this electrical power can be settled down at this
Yeah,
point?
that's a different point. That's a different point. Now, just see, practically, let me tell you, practically, we change the turbine mechanical power when we say that at this instant of time, this much will be the change in the electrical load. So if that means if we forecast at this hour the load is going to change, the electrical load is going to change, then just before that you change the turbine, you increase your turbine mechanical power. So as in this case, so if I say that at 5 o'clock our electrical load is going to increase, and then we are expecting a increase in the load now at 5 o'clock. So that means we can be ready, and then in that accordingly, just before that we can increase the turbine mechanical power. This is what we can say, right?
Okay, sir.
So same way, I can say that, let's say that at 5 o'clock we are expecting the decrease in the load, right? We are expecting a decrease in the load. So what we'll do, so when we say that at 5 o'clock we are expecting a decrease in the load, we will, so before that we will shift this line downward now. We will shift this line downward, and that way we can say that. So remember one thing, change in the generation that we apply in the power plant is based on forecast of the load uh, amount. So if we know that electrical load is going to change at this instant of time, then accordingly we change the generation. Otherwise, we do not change the generation most of the cases here. If we know the electrical load change, if we are expecting that at this hour electrical load is going to change, then we apply the generation change. Now here we have we say the word power dispatch. So what by the word power dispatch, it means that, let's say that you in a line you have 500 megawatt of power flow, right? And let's say that at this another instant of time you are expecting a increase load, then you will that just before that instant of time you will change your 500 megawatt to 600 megawatt, or you will change your generation to 700 megawatt, and that we call it as word power dispatch problem here. So in this case we change the turbine mechanical power here, right? But again, as in this case, remember one thing, we have said here that this turbine mechanical power we are changing in a stepwise. Turbine mechanical power cannot be changed in a stepwise, because that means you cannot suddenly increase the gate opening or the valve opening and suddenly the turbine mechanical power changes from 400 megawatt to 500 megawatt. 100 megawatt jump cannot be at t is equal to instantaneously, it cannot be in a stepwise. It will be as more or less like a ramp. So that means there will be a rate of change of turbine mechanical power with respect to time. Actually, basically it will not be as a step change here, right? So here we discuss more in detail about this criteria. Now at the point A here, right? At the point A, this is your initial condition, and PMO is equal to PEO here with an operating angle of delta naught here. Now we apply a sudden change in the turbine mechanical power here, right? And we change it to PM1. Now in this case, now this step 1, step 2, and step 3, they are referred from the previous slide only, right? So in the step 3, what we find it here, PM1 is greater than PE because instantaneously PE is at point A here, right? Instantaneously it is PEO, and turbine mechanical power is PM1, which is constant now. So PM1 becomes greater than PO, and thus we have positive accelerating power. And as a result, rotor accelerate here because this is positive, and thus angle delta will increase. So that means because of the accelerating power, angle delta is now changing in this direction here. So rotor angle will increase. Why? Because of the positive PA, excess energy is stored in the rotor during this acceleration. Because of the positive PA, you have more energy being, because rotor is accelerating, rotor is speed is increasing now. When the rotor is speed is increasing, that means you have more energy stored in the rotor during this acceleration. So during, as the rotor changes its position from delta naught along this curve right here, the energy is, excess energy is stored during the acceleration period here. Now as the rotor angle increases from delta naught here towards delta 1, towards delta 1 here. Now in the next case, this is the one, right? Now at point B, at point B, PE1 will be equal to PM1 because rotor angle has accelerated, rotor has accelerated and angle has increased to delta 1, and at that instant PE1 becomes equal to PE1, right, with angle delta 1, right? This is the one here. But next what happens now here, when PE1 becomes equal to PM1, you can say that accelerating power is becomes 0 at point B. So but at this point B, though the accelerating power becomes 0, but rotor cannot stop because rotor is running at a speed greater than omega s. When the rotor is running at a speed greater than omega s, rotor cannot stop suddenly at this point here, right? Rotor will continue angle and access. That means you will have an acceleration now. So that's the angle now, because of the rotor acceleration, angle delta now continues to increase here now beyond point B, and as such PE now beyond point B, PE becomes greater than PM here, right? So thus PE, because beyond point B, PE becomes greater than PM1 because PM1 is constant. So beyond point B, PE becomes greater than PM1, and as a result, you have it here. Now next one. Now this point, what you have it here along the PE curve, rotor will now deaccelerate. PE becomes greater than PM1, and when the beyond, that means along this curve, along this point, beyond point B, rotor will deaccelerate, but it will rotor deaccelerates. Now that means beyond point B, rotor speed now will fall back towards omega s. In fact, during this part, rotor speed was more than omega was. It was increasing beyond omega s here in this region. But in this part, beyond this one, rotor speed will now fall and it will try to move towards the omega s. That means it will deaccelerate towards omega s here, because along this side, accelerated power is negative now. So thus the rotor will deaccelerate, and as a result, rotor speed will now slow down, and it will slow down towards omega s because of negative PI. But still, angle will continue to increase up to this one, rotor angle delta. Yeah. So it will increase, rotor speed will slow down beyond this point B, but it will increase, angle will increase up to delta 2. it will increase up to delta 2. Because suddenly at point B, rotor angle cannot be stopped. And as it crosses this point, rotor will deaccelerate and the rotor speed will fall. It will try to reduce and it will move, it will try to reduce towards omega s here, but angle continues to increase up to delta 2 here. Now, whatever the energy which was stored here, now this excess energy during this part here, it will be now released. So that means the excess energy has to be given up by the rotor during this acceleration here. So here the energy was stored, and beyond the point B, whatever the excess energy was there, it will be now released and towards during deceleration, and with speed nearing to become omega, that means beyond point B, rotor will now slow down towards omega s here. Right? So if I say that uh, uh, omega s is 1500 rpm, right? So now omega s was 1500 rpm at this point. Now after this, let's say the speed is increasing to 1510, 1520, 1530 or something like that, right? So if speed has increased up to 1510 here, let's say, right? Then again, beyond this point, the angle is increased. Now after that, there is a deceleration. So now beyond this point, with the increased speed of 1510 rpm, now will reduce. So that means it will become, so during this period, rpm will now 1509, 1508, 1507 and so on. So but again there will be a tendency to oscillate here now, right? So as in this zone, now as a result, rotor will swing back here now. It will swing back. The rotor, in the previous slide, as I said, rotor has increased to this point, but you had deceleration, so angle increases up to this point, and the RPM has, let's say it was something 1500 and then slowing down now. So now after this point, rotor will swing back. It will decrease, rotor angle will come down. So what we have it here, rotor will oscillate to and fro in this way. Right? So that means it will come back here and then again it will go to this point, then again it will go to this point, and then again it will swing along this point here before settling down. Right? So it will now it also reaches, it crosses the point B, it does not reach to the point A, right? Then again, so here thus it will oscillate along this point here. This is what I can say. And then from the mathematics way, we have this one. So from this string equation curve, yeah, this difference in the power that gives rise to the rate of change of stored energy in the rotor mass here. So how much change in the accelerating power you have it here, either by change in the electromagnetic power or the change in the mechanical power. So that means the magnitude change in the PA will define what is the rate of change of energy here in the rotor mass here. And from this point, we can say that the area of acceleration, that means accelerating area, this is the difference in the power, and the accelerating area if we write in this way. So we have the change in the point from A to B, right? So the angle was changed from delta 0 to delta 1, and during this point, that means along the line A and B, we had actually delta 0 to delta 1 change, and during along the point A and B, you have actually PM1 minus PE here, because PM1 is more than PE. So PE can be any point along this line here now, and that is your area ABC here. This is your area ABC here now, right? And this is your accelerating area here, area 1. This is your area 1 here now. Similarly, beyond the point B here now, right? Because this was the, if you go back, this was the point B. So beyond the point B, we write another area. where you have the deceleration. So we integrate from delta 1 to delta 2 here now. We integrate from delta 1 to delta 2. But again, we write in the same way, PM minus PE, right? So you can say that we can argue that we can write PE minus PM, but we write in the same convention way. So we write PM minus PE, right? And then this will be the area, what you have it actually, sorry. In fact, this will be the area B, D, and E here. So it will be this area now here.
Sir,
So B, D, E,
sir,
and
from
this
the
is the area.
equation, sir, from the equation, it looks like a square area.
It looks like a.
Square. And
Why you say square?
because this is a, sorry, rectangular area, I mean to say that
Okay,
delta
you
E
include
length
this
and
part also.
PM1
You
minus
include this part.
PE.
You include this part also, right? Right.
What, sir?
Yeah, if you because in that case it is a square area. Yes, rectangle area, right?
We are taking
But
triangular portion.
yeah, I agree. I agree to it. Uh, but again, in that case, if it is a rectangle area, it means that you have this curve. You have this curve, very small region actually. Because overall, if you look at this curve, this is a non-linear actually. So I can say that at least up to this point, the curve is linear. All right. But if you consider beyond this point, yeah, the curve is more or less like a non-linear here, right? So in that case, it will not be a rectangle area defined here, right? Now we will discuss more in detail later on. If I say that this line, what we have said, angle delta 2 is shifted to this side. This angle delta 2 can be somewhere here. It can be here or it can be here. So in that case, this area, it will be, we will, if I say this line, what we have it here, it is this one, right? So we will have the area above PM1 now. So if you have this area line over here, so in that case, it will be all the area above PM1. So this will be the area A2 and this will be the area A1 here now in that case. So that's what I can say here. Right. So now we want to understand more in a mathematics way about the equilibrium criteria. So from the swing equation, the relationship that we have, what we do some manipulation here. So from this equation is manipulated by multiplying this term du delta by dt and then rearranging. Right. So we have written this term after multiplication and then using this relationship and then further multiplying by dt and then we write down this equation here. So what we have actually, this is the inertia part and thus we manipulate this relationship in this form. So it is actually d delta by dt. That means rate of change of rotor angle. All right. And this rate of change of rotor angle is with respect to your reference, right? So this rate of change of angle is actually given by this relationship, which is actually the square root of this, because omega s by h, this is constant. And then what is the change value of integral area actually? Now again in this equation we have said delta, I have here delta c. At the moment, let us write delta only because delta C can be any. We will discuss more in detail later on what is delta C, right? So in general, we write this rate of change of rotor angle position given by this relationship. And what we find here that it is this one. That means uh, integral of the change in the power, integral of the change, that means you can say the summation, or in fact it's not the summation but the integral. That means you continuously integrate, you continuously sum the difference in the power, of between mechanical power and electrical power here actually. You do the integration from between the two angles actually, delta 0 to delta 1 or delta 1 to delta 2 and so on. So you integrated that part here. So and that will define what is the rate of change of angle position here now, right? And from this about relationship, this is actually the it says about relative rotary speed with respect to synchronously revolving reference frame. There is a spelling mistake. It is synchronously revolving reference frame. Refer to the previous slide. So we have defined one revolving frame which was revolving at omega s. So this rotary speed, that is the rate of change of rotor angle position, is with respect to synchronously revolving reference frame. And for stability, this change must be zero. The speed must be zero after some time, right? And thus for stability, it is important that the integral between the angle, all right, between the angle, the difference of the power must be zero, whether you have acceleration or whether you have deceleration, right? That means whether you have delta p plus pa or minus pa, right? Both should become zero actually. That means the area which we have defined in the previous slide, that should be equal. Then only the system will remain stable to the new operating point. Otherwise, no. We will discuss more in detail later on. Now, if I say that, if I say, for example, because if you go to the previous slide here, as I said that if I have this line, if I have this line here, right? If I have this line shifted to this side, let's say I have it here somewhere. That means rotor angle has increased to an extent somewhere here, right? Then in that case, what will happen? Let's say that it has increased to this one, right? So when we have this one, rotor angle is much larger. Rotor angle delta 2 has increased to this point here, right? And in that case, what you have it here, PE is less than PM. But beyond this point, this is the another operating point here. Beyond this point, the PE will go drop to zero. And then that means the generator will lose the synchronism with the system. That means with the load, with the line actually. So, so that means in this situation, here because the area 2 is deceleration. So if you have the angle increased to this point, all right, and let's say the rotor angle was continuously increasing, and then in that case it reaches to this point, whether the mechanical power is constant now, but in that case area 2 becomes greater than area 1, and then with the a change in the area, change in the angle, with the increased angle beyond this point, it will result to PE less than PM, and as a result the machine will lose the synchronism here, right? It is this way here. That, so we will discuss more in detail later. And let's say another one here. If I say that this P change in the turbine mechanical power was not here, but it was somewhere here. It was less because this line I had it here. If I had this line shifted to, that means if I increase the turbine mechanical power by a large magnitude, then this area, area 1 will be this one. This will be the area 1 here. And as a result, the deaccelerating area, you will get only this much. All right. You can have, even if you have the angle increase up to this point, the deaccelerating area will be this one. However, area 1 will be this one. And as a result, in this case, area 1 is more than area 2, right? And that means whatever the energy which was stored during the acceleration, it is always more than deacceleration part here. And as such, again the system will lose the synchronism, and then it will be again the instability here. We will discuss more in detail later on this part. So thus it is important that now here thus if we have considered the instability example. So if in case in fact I'll skip this part here, we'll discuss more here because this part, if in case area 1 is greater than area 2, that means the area of acceleration is more than deceleration here, right? Now generator load angle will it is possible that you may have TM PM, as in this case is greater than PE, and thus you have accelerating power PA being positive here. Now generator will therefore, in the previous case, it will accelerate before it slows down completely, and thus it will become unstable. And as I said earlier, with another example, if in case area 2 becomes greater than area 1, so that means deaccelerating area is more than accelerating area. Every in that case, the machine will deaccelerate and completely before is accelerating again. So that means PE will drop to 0. So again, in that case, it will never reach the actually attain the steady state. Now, if the two areas are equal, A1 is equal to A2, then we say accelerating area is equal to deaccelerating area, and this will define the boundary of stability limit here, right? Here we have one of the, but I will have it discussion for a few more slides. Now, let's say that we have a generator, and then we have the or we have the two lines here, and then connected to infinite bus system. Uh, I will give you a problem on this, so you think over it, right? So you have a generator supplying power to infinite bus. We have two lines, two parallel lines here. Consider the synchronous machine is initially operating at a steady state, and thus electrical power is equal to mechanical power, right? That's the part here. Now, here we have the equivalent circuit drawn. So we have a voltage source. This is the reactance of the synchronous machine, and this is your generator terminal. This is the reactance of the transformer, and then the two reactance of the line here. And this is your reference voltage on the infinite bus side. Then we can determine what is the equivalent reactance here on the circuit side, line circuit, and including the transformer. And then we can get the equivalent circuit out of this, and we write in this way. So now we want to have the power transfer from generator terminal to the bus bar here, right? So this is your reference voltage, and this is your reactance part, and this is your voltage source here. And we want to know what is the electrical power when we have it here. So even for this system, we write the same way from the relationship. So now it will be the product of in fact, if you want to determine the power flow from the machine part, from the internal machine, so we consider the excitation EMF here, this one, and we write this part, and then we have XEQ. In fact, this SEQ will be actually including this part here. Remember one thing, this is XEQ completely. So we have this XEQ written here. So in fact, XEQ will be equal to X1 and X2 in parallel with in series with S transformer and XD prime here. So this is your XEQ, and we have this P delta characteristic, right? So here in this case, you try to understand if there is a fault here on the line, what will be the dynamics change here. Try to guess on this part here. So I will stop here. If you have some query, then I can I can address to it, right?